Lecture 7, connection, wedge, product, and cross product. You see, this is analogy, okay, between the wedge product and the cross product for form 2. Now, consider the cross product U cross V, where U is UI, EI, and V is VJ, EJ. Now, EI dot EJ is delta IJ, which means orthonormal basis. Okay, this is Euclidean space, Cartesian space. Now, the cross product UV is U1, U2, and 3. U1 because U1, U2, and U3. These are the components of the vector U and V. So this is the determinant, okay? Now I can expand this determinant as, in this case, U2 V3 minus U3 V2. So you just cross here, you see? Cross here, and this is equal to E1. Now, E2 and E3, you just rotate this, okay? U2, after U2 comes U3. After V3 comes V1, U3, U1, and V2, V3. Now, E1, E2. Again, you rotate here. This 3 is 1, this 1 is 2, this case, okay? U1 is U2 and V3 is V1, E3. You see, I mark the blue one according to this picture here, this figure here. You see, this is parallelogram, the green one, okay? It's a vector n, normal n, to the plane U cos V. You see, that's a vector n, the normal. It's not necessarily unit vector, so this is a vector n. Now I project this vector here, this cross product, on this plane x1 and x2. This is the blue one. You see, that's the blue one. So the projection of this, okay, this U1, V2, V1, U2, and E3. I could project in the other planes, you see, plane x2, x3, or x1, x3. I just emphasize this one, the blue one. Project area on the plane x1, x2. E3 is the unit normal, okay? Now, N is U cross V. You see that's a normal to the green area. See, that's the green area over here. You see, this N is normal to this one. Now, that's step 1, recap. You see, I always say that tensor is a map. You see, what kind of map? You see, this is alpha, belongs to the cotangent space. It acts on U, which belongs to the tangent space. This leads to the real number. That's the definition of a tensor, okay? Thus, alpha, okay, is a covector, okay? It's alpha I dxi because it belongs to the cotangent space, acting on uj partial xj, which lives, okay, on the tangent space, okay? Now, this is alpha I uj dxi partial xj. Now is alpha I ui because this over here is delta ij. You see, this over here is delta ij. So this is alpha I ui. You see, it acts on uj and put ui. You see, this here is a real number, okay, as the definition, okay, of a tensor. Now, that's beta is bi dxi, and the vector vj partial g, partial xj, is the same. You see? You see, this is map, the map. Beta belongs to the cotangent space, a v to the tangent space. It acts on the v and leads to a real number, by definition of a tensor. Now, then, I will work with both bi dxi, vj, partial xj. Again, this bi, vj, here, you see here, is delta ij. You see? Let's write here. Delta ij, okay? It acts, okay, on the vj and set vi. This is a real number also, by definition of a tensor. Now, consider the two form 1, alpha and beta. Alpha belong to form 1, and beta also to form 1. See, both belong to the cotangent space, alpha and beta, like here, you see. So, now let's take the wedge. The wedge acting on UV by definition of a tensor. This leads to a real number. You see, now I'm working with the two forms, alpha and beta. Now, alpha and beta UV is alpha act on U, beta on V, minus alpha on V, beta on U. Exactly is a connection between this over here. You see? Exactly what I obtained. That's why I wrote clearly that this is in this case, okay, there's a real number. That's a connection, okay? Analogous to the cross product in Cartesian coordinates. Now, that's alpha dxi and beta dxj. So the wedge product dxi dxj, wedge dxj, apply in the UV. This here is a two form that belongs to the cotangent space, and the basis UV are the vectors that belong to the tangent space. Now, by definition, see, dxi is applied to the vector in TPM. dxi belong to T asterisk P, okay, T asterisk P, and because it's cotangent applied to the tangent, this to a real number. So dxi partial dxj is delta ij. This is dxj partial dxi is delta ij, which is a real number. This is a real number. You see? Now, the wedge, okay, I always apply dxj, okay, in this case. So, dxi wedge dxj, I just substitute, you see, alpha and beta just over here, you see, on this line here. So, this is a bilinear. Why bilinear? But it's linear in each argument, okay? It's linear in each argument, so that's a bilinear. Hence, dxiu, you see, this is ui. dxjv is vj. Finally, dxi wedge dxj apply in u and v is ub. ui vj minus vi uj. Now, if I is equal 1, j is equal 2, you see, this is the connection. dx1 where dx2 is 1v2 minus v1 u2. You just look here and look the blue one over here. So I could project in other planes. You see, I just set, for instance, dx1, dx3, dx2 and dx3. I just substitute on alpha, this like the other project area. See, that's clear. Again, I recommend you just to copy everything here. Try to write and study, okay, and try to do by yourself. Then you're gonna grasp, okay, this important concept between the connection between wedge product and the cross product. That's okay.